that kind of guy. I guess it was bad weather out there. That's why people aren't here. Or I'm not stimulating enough, one or the other. Can't really tell. All right, E6 has asked for feedback. They would like essentially they would like an I like list from you and an I wish list from you. So want to just like brainstorm it out here? What'd you like? It was nice. It was nice to go. Interactive. We didn't just stand and listen. Yeah. Okay. What else? No homework. No, not gonna write that.
It was nice how we started in lobby, went into the pre-production, which is like the monitoring room, into production, something in the focus for the sun. So like we sort of took a lot.
Yeah.
Much better than having.
Yeah, I agree.
I like the guides, they're pretty endearing. And they actually like work there.
And they were actually engineers.
Yeah, exactly.
Yeah,
So
no,
they knew what
all
they were
of the-
talking about.
All of the things I asked for, they delivered, that's for sure. Yeah, sometimes we get like human resource folks walk us around, which is fine. They know the facility, but if you ask one question, they're like, I don't know. We'll have to get back to you on that. So these folks seem to be able to answer any question. Good. All pluses. All right, would you wish? Yeah, sound was a problem. Yep. It was very loud out there. It was hard to hear. Yeah. Yep. And originally I thought actually they did a good job putting us into groups, but then you couldn't hear unless you were the first three right in front of the guide. Then the next four were like, no, couldn't hear that. So that was good. Okay, what else?
Seeing the actual spaces, like there's an office space.
Yeah.
And we nice to at least lay eyes on that, get a feel for where they're really working, they're locked in.
Yep. Yeah.
There was one upstairs too, but visually, we're not allowed to see that.
Yeah. There was an upstairs, and I'm guessing that's where their cubicles were or their offices, whatever they have. Yeah. It's nice to see though, like, and honestly, every field trip, it's different. Like you go into Leatherman's engineering office and it looks different than I'm sure an E6 office. And then I was just at Marx Brothers and they took me into their one engineer's office. And it was like, I don't know, I've never seen so many big screens on a computer that were all curved. So his desk was round and his all these displays were curved and huge. I was like, whoa. I don't know, man. It was like, it was cool, but I wouldn't want to sit in that little focal point for 8 hours. All right, what else do you wish? We're doing I like and I wish on the field trip if you just walked in. So E6 has asked for feedback from you, not from me.
I think the things that when like drink confidentiality that they were talking about, because there's probably a lot of things they can't tell us, but they'd rather would.
Yeah, I think the only thing they didn't answer that I asked was actual production numbers. I was curious how many they're producing like per month. And I got a lot. Was the answer. Did it? That's all right.
Those long discs, I asked what they're made of this. I don't know.
Oh, our guide told us they were tungsten. Yeah.
So you guys know.
Oh, that's interesting.
But it would have been nice since we were at the monitors and we were doing data reviews and everything. Since they know we're in an engineering class, it would have been nice to dive into that just a little bit more.
Yeah, I think this might be like the differences in the tour guides, because our person like went deep
Oh, really?
and I was thinking, this is like,
It's too deep.
was like way over, yeah, it was like way over our head at times, and he was just like feeding on it, like he was going off, right? Yeah, no, I tracked a bit, and then I was like, okay. No, he got over the top, which part of me liked because he was so energized with what he was telling us. I was like, oh man, this guy, he loves it. Like he's really into this. I mean, this is the kind of energy you want when you go to work. Like you want to be that happy. It seemed like he was super happy in his environment. So
Okay. Like, not bad, not good, but maybe to explain the big stuff.
Yeah.
Like I said.
Right. What about time? More time, less time? Time was good. Yeah, yeah. Good. It was close. I like that. I didn't make you drive downtown Portland or something. We've been to a lot of further places away that's complicated. So I went to the Bonneville Power Administration at Cascade Locks. Went through the dam. It was a super cool tour, but that was solid 4 hours. So, and we didn't get engineers. Like all that work to set this up, and then we just got like Ranger Rick walking us around, and it's like couldn't answer any questions about the turbines and the generation systems and the backup systems. Yeah, it was cool. It was cool walking through, but man, we left with a lot more questions than we had. All right, I think that's pretty good. Any questions about anything else so far? Like, you're supposed to be working on the project. That is correct. All the time, day and night. You should be working on this project. There should be no other classes that you have other than this one. Yeah.
Is there some kind of specific documentation during the prototype build?
Nope. Prototype build is literally bring in a functioning prototype. I will ask you what questions you're trying to answer with your prototype, because that's why we build a prototype, is we are not sure of our own design, or we just want to confirm that this design is going to work, right? So we build a prototype and we go, oh, that didn't work, or this has potential to work. Yeah. Okay. That's why we do a prototype. That's why you're doing it. So I'll ask you, like, what questions are you trying to answer through your prototype? That's it, pretty much. And then you demonstrate it. It's supposed to be a functioning, usable prototype. Doesn't have to be the whole system, right? It can be a subsystem. It can be just the grabber that holds the ball, or it can be how you're going to get the ball over there, or it could be the structural piece that's going to hold all this stuff together, or it could be the two pieces that have to come together and how that's going to work. So there's a lot of different areas of this little project that you could prototype. I mean, obviously, if you prototype the whole thing, you're ahead of the game. That means you're already into testing, and that's a good thing. You want to get to testing as fast as you can. That allows for design and redesign and redesign and testing and testing. Yeah, good. Anything else? Questions on anything else? We have guest speaker coming up on Thursday, so you have that little pre-guest speaker, like put your questions up thing that some folks just cannot figure it out, but you all can. EPA? I don't know. He just said he's going to bring us an army of electrical engineers. I'm like, oh, okay. Sounds good. I know they're recruiting, like this is a recruiting mission for them. So I guess if you were looking for work, have a resume ready, and you probably quit school and go to work right now as an electrical engineer or something. I don't know. They're hungry. That's all I know. They'll take warm bodies that actually can show up to class. They'll take you. I don't know. They could have internships that, BPA is a big creature. So who knows?
Looking at BPA, and we're going to determine the focus.
Yeah.
A bunch of stuff on Bookville.
On what? Yeah.
And so they're just the company that surrounds that, or they do.
Oh, they do extra. Bonneville Power Administration
Yeah.
does a lot.
Okay,
It's
so
a giant organization. I mean, Bonneville's a big part of that project, but they're into distribution, not just, manufacture of electricity, but the distribution of the management of the river, like on and on and on. Yeah. It's a big group. All right, so coming up, we have the prototype on the 23rd. We've talked about that a little bit, but there is a structural analysis document coming up. So I need to give you some structural analysis knowledge. So you have something to build this document out of, okay? So we don't want the project just to be trial and error, although trial and error is probably your number one design tool right now. You're gonna have an idea and you're gonna try it and it's gonna error and you're gonna fix that error and then you're gonna try it again. So trial and error is just a loop within the design loop, right? And there's not a lot of engineers that will admit it, but we do a hell of a lot of trial and error out there. We like to calculate things, but that's just forecasting. That gives us an idea of what we should be using, what the loads are, and a solid estimate as to what is going to happen. But then we use trial and error to make sure things are not going to just blow up on us, right? So we do a lot of trial and error, but we want to try to do some calculating on our project and create a analysis of something. So I'm going to give you some tools for that today. And it's going to be a lot. So I'm going to go fairly quickly through 2 classes that you're going to have in 1 hour or less. So what I'm hoping for in your production of the structural analysis paper is a very simplified analysis of what you're building, what your system is, okay? And how it's going to handle those loads. All right, so let's do that. I'm going to show you, I put up on the home page a document that is used in the engineering department. I put it in week 6 today. It's called the engineering format. So this is similar to what your document's going to look like because I want it to be calculation based, right? Now this one has a lot of notes on it, make a neatly drawn sketch or diagram. So that actually is not part of the document you're going to produce, right? These are just notes on how the layout is typically of calcs that we submit. And we submit a lot of hand calcs and we submit a lot of computer-based calcs. So we do both. This is an entire hand calc package. It's from 1996. It's of my home that I currently live in, the one I built, right? But the structural engineer did it for me. And you can see that he was a professional engineer because we keep talking about the stamp, right? That is the stamp. And it's literally a stamp that you get when you pass the PE. So that means that Mr. Dowler is 100% responsible for the structure that I live in, right? At least the design. I built it, so I had to build it to these specifications for him to be liable. So that's where the fight comes in. If I missed one anchor, if I missed one set of nailing correctly, if I didn't put one shear wall in correctly, he's released from his responsibility because it wasn't built to this specification. That makes sense? So that is the stamp. So I'm going to make you all stamp your calcs when you get them done. I'm kidding, but I'm not ready for that yet. All right, so this is kind of the format that we use in our calculation-based courses. So it might be similar to a math format if you have a math class. If you've not had a calculation-based course yet in engineering, you'll see this when you get there. Some of you are in my statics class. This is what those homeworks should look like. It should be a neat sketch. That usually means a straight edge, but notice it's not crazy detail, right? It's just a simplified schematic of your system or whatever you're doing the calcs on. Simplified, right? But that's where it starts. And then there's some kind of problem statement. So when you do it, you should have some kind of problem statement. Like I'm trying to calculate the structural piece that is going to hold the 4-ounce weight, as it travels across to the delivery point It's got to get over there somehow, right? Maybe it's like a fishing pole thing, or maybe it's like gonna land on the table and then a conveyor belt across, or whatever it is. Give me a problem statement, like this is what we're trying to calculate. Theory, probably don't have to do that yet. Any assumptions, probably don't have to do that yet, but then the solution is here and it's laid out kind of top to bottom and left to right. Okay, so when you do your calcs, it's just like we write on a piece of paper. It's left to right, top to bottom. We don't normally want something that we've calculated at the bottom of the page and then we reuse that again at the top of the page. That's confusing. Someone's going to look at that and go, I don't even get what's going on here. Like, where that number come from is often what like happens. So I'll show you these calcs. So this is on there. You can kind of get a feel for it. It's just really neat and tidy. That's really all we care about at this point. So here's his. This looks like a wind analysis, south side, west side short. This must be a west side short wall. And then he's just flowing right, left to right, top to bottom, just going to work his way through it. Okay, these are all shear calcs because this is a lateral load document. Lateral load is the structure doing the lateral deflection, right? Like a wind load or seismic, although he's very careful not to put seismic on there. So he doesn't want that responsibility. But again, just fairly nice and neat and flowing through the equations. Shear is V. So we're not going to do shear today. We're going to do bending, but that's all right. Make sense? Kind of like the flow and the image of what we're looking for. All right. So you're probably going to end up with these pieces of the structural document. You're going to end up with a free body diagram. That's what this is called, free body diagram. And that means we're going to take a system and just draw it and put the vector loads on it. So the example I'm going to use is this one right in front of you where I have a beam laid out between two supports. Like if this was yours, I think we're 8 feet apart. Is that correct? Yeah. So let's say it's 8 feet. I think this is a bit longer than 8 feet, but that's all right. But the free body diagram for that would look something like this. Simplified beam. And then over here at this point, the object has weight, right? It's acting down. So all these forces we want on the free body diagram. So the weight of this thing, I'm going to say is 2 pounds. Okay, we have scales. You can weigh stuff. So your numbers will be real and you should weigh them so you can draw a good free body diagram. But anytime we put in the weight of an object, anyone know where that goes? Ben's not here yet. He's got to take a few hours to wake up. He told me that yesterday. Weight of an object. So the weight of me, if I was going to stand on this table, like where do we put my weight? Do you think it's going to be like out here on my arm, hanging down? It's going to be what? Yeah, it's going to be center of gravity. Exactly. Geometric center, right down through the middle. Okay. And that's an approximation even because I'm not homogeneous. Anyone know what homogeneous means? The same throughout. I'm not made of the same material. I have all these different kinds of materials in me. Even this piece of wood is not homogeneous, right? What's different about wood? What's it have? Yeah, grains, knots, all kinds of deformities, right? It is not homogeneous. We like to say it is, but it's not at all. All kinds of defects in it too, like all kinds of defects. But for this analysis, we're saying it's homogeneous. If this thing weighs 2 pounds, then I'm going to take the 2 pounds and I'm going to put it through the geometric center. 2 pounds. We put it in as a vector, which is just a line with an arrow on it. Okay. That's a force vector. Now what's happening at both sides? Because this thing's just sitting here, right? It's not going anywhere. There's supports on both sides, right? So there's these. So the table is pushing up and pushing up. So this thing called equilibrium means that all the forces in all the directions are equal to zero. If they're not equal to zero, something is just flying around, okay? If I didn't have gravity, I'd just fly around, right? If I weighed too much, I'd sink into the ground. If this building weighed too much, it would sink into the ground, but the ground must be doing what? Pushing back up to hold the building in place because it's static currently. Right? So how much has to be here and here? We're kind of symmetrical. We got 4 feet and we got 4 feet. So if all the forces in the y direction have to be equal to 0, how much does this have to be? Roughly a pound. And probably not roughly, it's got to be exactly a pound, right? For this to be true, and we write that some forces in the x equal 0. That's equilibrium. Some forces in the y equals 0. That's the case we have. And then there's this thing, sum of moments equals 0. Anyone know what a moment is? Yeah, that's what we would, that's what some crazy normal person out there would think, but engineers, we think differently. We have to name things special. So no one else knows what we're talking about. A moment is, so some forces in the x, everyone knows the x direction, right? Positive x is where? That way. Negative x is that way. So forces in the x is lateral movement x direction. Forces in the y is what? Up and down. Yeah. So those are the two translational forces and directions that we have, x and y. But there's another effect that happens due to forces, and that is rotation. So a moment is a rotation, better known as a torque to most people in the real world. A torque. So that's like put a wrench on a bolt, put some force on it, and it rotates, right? So that's not translating the bolt this way or this way, but that's rotating it. Those are the 3 effects that we deal with. If all of those are 0 on this structure, it's not moving. If there's an extra moment somewhere, this thing is tipping over. If there's extra y forces, it's sinking into the ground. If there's extra x forces, then it's like shaking off its foundation. Okay, but that's it. All of those. Ben. At some point, I'll probably label it up. Yeah, because we're going to have to do more shenanigans. Yeah. Ben would like me to label all my points. So I have a point A, a point B, and maybe a point C. And it's not a bad idea because then I can say, hey, let's look at C, or hey, let's look at A, right? Okay. But that's a free body diagram. All right. If you're going to take your 4-ounce weight and put it on the end of a stick and then just like go like this and hang it out there, everyone follow me, like a cantilever or a fishing pole type thing, then the free body diagram looks different. It's still a pole, and we still want to draw it snapshot in time, that maybe here's my 4-ounce weight. I'm going to call it 0.25 pounds, right? So a free body diagram is just a snapshot in time. And it's usually the worst time, like the worst loading condition. That's why I drew it like this. I didn't draw it straight up with the 4 ounces hanging straight down because that's not a bad loading condition, unless your pole is super flimsy and then it buckles, but that would be a whole different analysis, right? So I draw it in the condition that I'm really worried about, that condition. So what's fighting this down force? Yeah, whoever's holding it is putting in an up force. And how big would that have to be? Oh, we should probably add our 2-pound structure. Right? Still weighs. I'm going to use the same structure. So how much is coming down? 2.25. So how much has to go up here? Same thing. Right? But what else is happening? There's no up force out here. What's this pole trying to do? Probably bend, but If we just kind of didn't support it, what would it do? It would rotate. It won't fall because we're still going to give it this like up force. But instead of like my arm holding it out here, if I just kind of let go of it, it's going to rotate. This thing wants to rotate. All this wants to rotate. So then we have to fight it with what's called a moment. So cantilevers, this is a cantilever where there's no support out here. We have to have a support system that will fight that moment. You know, if you're fishing, it's you holding the fishing pole. If you let go of the fishing pole, the pole rotates, is gone, right? The whole structure also has to resist that rotational effect. If it doesn't, then it breaks, right? And out here at the very end, there's no rotation. That's just a free end kind of dangling out there. But as I walk it back, that moment gets bigger and bigger, that rotational effect, until I get right here where this moment is huge. That makes sense? Just in super basic, kind of like, hey, this is how a fishing pole works. This is how a cantilever works. This is called a simply supported beam. It's got supports at both ends. This is what we do. You drive across a bridge, you're hoping that that is simply supported at both ends with enough foundation there to carry the weight of the bridge, which is way more than you and your car. The weight of that bridge is enormous. So the overall structure of a bridge is really to hold itself up and then let you all go across it. Doesn't really care much about that. Okay. Simply supported bridge, correct. Yeah. So really what we do with bridges, let's talk about bridges, because that's another area that I wanted to hit on, because they are typically built out of what? Yeah, very few are just like straightaway beams. You'll go across a few that are just the smaller bridges, that overpasses, that are just big concrete beams, right? Massive concrete beams, have no upper structure to them. That's just a beam bridge, right? Those are usually smaller. If you're going to cross the Willamette, then you're going to go across something that is going to look maybe like a triangle. So maybe it's one big truss. We call these trusses or triangles. Or maybe it's a collection of, you know, all kinds of little ones. So for the sake of time, I'm not going to get too fancy with my drawings, but there's all kinds of them, right? Right, and then we can even drop some verticals in. Sometimes we don't drop verticals in, but then we're going to simply support it. Right, this is no different than this. The worst case scenario for loading condition is a big load right there. The entire weight of this bridge acts through the geometric center. Okay, and then when we drive our car across there, and actually we don't use cars, we use big semi trucks typically. But as we drive whatever we're going to drive across there, we put it right in the middle, and that's where we do our analysis. So for example, the large bridge downtown Portland, why can't I think of the name of that bridge? Our biggest one. Not the Fremont, maybe it is the Fremont. Maybe it is the Fremont, the giant one. Yeah, the double decker. Yeah, that one, its loading design condition is our worst snowstorm, our 100-year snowstorm. So we put a bunch of snow and ice on it, and then we line it up, upper deck and lower deck, with the heaviest semi truck that is allowed to go across it. Stacked up traffic jam, full on. That's the loading condition that that thing's designed for, which it'll never probably see, right? But if you go across that bridge and you ever get the chance, like in a traffic jam and you're stuck on it and the other deck is still moving, like if your upper deck stopped and the lower deck is moving, that thing is bouncing solid 3 inches up and down, just like really flexing nicely. Super creepy, but it's cool. Yeah, so we designed flex into them, right? But notice what it's made out of, triangles. So if you're having rigidity problems, think about adding some upper structure or triangles. That will help your design. Okay. I'm not going to go into any analysis there, but when you take statics, you'll learn how to transfer all these loads through the structure and calculate it. So as we do that, as we learn that, then we look for the highest loaded. So maybe it's this member that's the highest loaded, and then we design to that highest loaded member, right? And then we make all the members typically the same. Some of these top chords might be smaller, some of these bottom chords might be bigger. But that's essentially what you learn in statics, is how to transfer those loads, both through a structure and through a truss system. Because that, if you crawl up into your roof, most of your roofs, if you're in a home or even an apartment, if you get all the way up to the roof, that's going to be a truss of some kind. That's what we do. All right. The other thing is bending stress. So this is a calculation I hope you do. So we need to talk about bending stress. This is S for stress, B for bending. So some will use sigma. So the Greek letters come into play real quick in engineering. So when you go through your statics, your strength, your dynamics, your fluid mechanics, you get a lot of Greek variables. I don't know where that came from, but we've done that forever. So some books will use S for stress, some will use sigma for stress. B would refer to bending stress. So going back to my simple system right here, and I'm going to stick with 2 pounds, 2.25, because my little ball, my 4-ounce weight is coming across and I'm stopping it right in the middle. That's kind of the worst loading condition, right? So now I've gone to 2.25 pounds and I have 4 feet and 4 feet. Okay. Bending stress is MC over I. So we have to understand the 3 variables that are in bending stress. The reason you would calculate a bending stress is you would want to compare it to a material. So if I'm using wood, right, I can look up Doug fir allowable bending stress. Like the wood industry has dialed that in for me as an engineer. The steel industry has that dialed in for me as an engineer. They know the stresses of all the different alloyed steels out there. Strength of materials is where you'll learn all about those, right? But what we do is we calculate a stress and then we compare it to something. If you're using cardboard, you got to find the stress, bending stress of cardboard. There's some out there. There's not a lot of great data out there. So find what you can and use that as your comparison. I'm going to do it to this wood. And I'm going to call this wood Doug fir. It's a common wood in our area. And the allowable bending stress, so SB allowable, I'm going to say is 900. Yeah, so stress is in what? Check that out. What is that? Pounds per square inch, also known as PSI. It's like a pressure, right? And it is a pressure. It's an internal fiber pressure. It's a pressure on all the little fibers of Doug fir. It's not very high. 900 is pretty darn low, right? If we think about mild steel, 36,000 PSI. Much different. Steel's a lot stronger than wood. That makes sense. But I have an allowable limit of 900. So I have to figure out, like, based on this load condition, how much bending stress is there on my little piece of wood, right? And then I make that comparison. So if I come up with 900, what do you think? If I come up with 900 PSI of stress on my wood and I compare it to 900, is that a good or a no good? It's no good because we're right at the limit. Yeah, so maybe good, but with no factor of safety at all. 0 factor of safety. Well, just so you know, the wood industry's already done all that factor of safety for us.
So that's-
So we can go right to an allowable when it's given. That industry has done all the factors of safety for the material. Now, that is right at the max. With wood, I'd probably go for it because they put crazy factors of safety on wood in this country. Not other countries, but in this country, right? So I'd go right to the 900 for sure. In steel, not so much. If I was at 36,000 PSI for my bending stress on a piece of steel that is limited at 36,000, that is a 0 factor of safety. That's not cool. We like a lot of factors of safety. The aircraft industry, how many factors of safety do you think there are in the aircraft industry? Yeah, there's lots, but a basic rule of thumb, if you're designing a part for an airplane, is 10-to-1. And then there's always redundancy. There'll be another part that can carry that load. So there is at least double redundancy and a factor of 10-to-1. And they're still trying to make them as light as possible. So that industry is tightly controlled, like a lot of industries. But what do you think the factor of safety is on my little video camera? Like, it's got an arm, it's got some load, some stuff going on there. It's complicated, right? What do you think the factor of safety is there? Yeah, I'm guessing there's none, 0. In other words, if the little head fell off, is it going to kill anyone? Probably not. Is it even going to hurt me? Probably not. So if there's no life threat involved or bodily harm involved, factors of safety really go away. Phones have factors of safety, yeah. All kinds with like heat and all kinds with like microwaves and all that kind of stuff, yeah. Everything's probably got factors. Anyway, let's keep going because we got to get to this equation. We got to still understand this rotation thing. M is moment, it's the rotation. Okay, so the way we calculate this is we have to find the moment based on the loading condition. So from our free body diagram, we have to find a moment, and then we have to calculate a C, which is very easy. I'll explain that. And then we have to do inertia. And when everyone thinks of inertia, they think of like moving parts. This is not moving parts. This is static. It's equilibrium. It's just sitting here. It's doing nothing. So this is what we call area. So it has to do with the cross-sectional area. Does everyone know a cross-sectional area is? So like you have a tree. For some reason I'm doing trees today. You have a tree growing, right? And I take a saw and I chop it in half. What's that area look like? Yeah, it's round, kind of round, right? That's the cross-sectional area. So here's my beam. What's the cross-sectional area look like? Yeah, I don't even need the dimensions, but what is the shape? Is it square or is it rectangular? Yeah. Yeah, so that cross-sectional area looks like this. Right? In that position. So the other position it could be in would be like this. Everyone get that? That's cross-sectional area. So both C and I deal with the cross-sectional area because the cross-sectional area is so important to its ability to resist bending. And that's what we're talking about, resisting bending. Okay, so notice that C and I have nothing to do with what it's made out of. It's just the cross-sectional area. That could be a piece of aluminum that is of that same shape. And we're going to say it's 1.5 by 0.75 inches, okay? Right? Cross-sectional area, that's all that is. C and I deal with this cross-sectional area. This is area moment of inertia, I, and you can look it up for any shape. It's very simple equation typically. So if you have a beam kind of like this or something similar, simplify its shape. If it's complicated, just simplify its shape and calculate an inertia, right? An inertia for a rectangle is base height cubed over 12. I could have looked it up. I didn't need to. I use it all the time. We are addicted to the rectangular shape because if you're going to use a wood product, it comes in a rectangle typically, right? And we use a lot of wood products. That's why all our trusses in our houses are made out of wood products. Yeah. So this gets calculated. That's this. This gets calculated from the shape. Okay. So here's a rule of thumb. The higher the I value, the better resistance to bending. So this is just talking about shape, not that it's made of wood. Could be aluminum, could be gold, could be diamonds, could be whatever. I don't even care because inertia doesn't care. Inertia just deals with the shape. Okay. The higher the inertia, what? Better resistance to bending. And we want to resist bending. That's what we want. So if I calculate it on this shape, that's the current shape. I have it in that position. Agreed? Yeah. So what is it? What's the base? 1.5. What's the height? Get your calculators out. Divide by 12. Come on, this is it. This is a gold mine. After this class, you can go out and make some money doing this. Well, maybe not yet, but soon. What's my inertia value?
0.05.
How much? 0.0527.
0.0527.
So you went 1.5 and you went 0.75 and then you took it to the third, correct? Why do I get, what, did anyone else get a number? What?
Yeah,
0.05? 0.05. And what are the units?
That's
Inches, unit list down below. Weird. What happens to these inches?
that's inches.
That's inches to the third, and then we multiply by. Yeah, who's got Favreau for class? Anyone got Favreau for class? Dave Favreau? Who's your math instructor? Favreau. Yeah, you got him? Ask him what inches to the fourth is. Yeah, I tell him Donaldson needs an answer. Wants to know what inches to the fourth is. That's the unit of area moment of inertia, right? And if you look in the book, it'll say this is a very abstract unit. It is super abstract, right? So small number. How do you think it does in bending? Not very good, right? Let's do it in this position. Right? That's just taking this and putting it up on what I call the strong axis. What is it over here? Base is 0.75. Height is 1.5. You better figure it out. You need a calculator. So 1.5 to the third is what? Right, 0.75 times, no, you're probably right. 12 divide, I get 0.21. Anyone else get that? 0.21?
Yeah.
Yeah. Like magnitudes better. Still a super small number because this is a tiny little beam. But everyone agree that the 0.21 is like not just a little bigger than 0.05, right? This is 50 thousandths. This is 210 thousandths. So we're talking magnitudes bigger here. This should resist bending, correct? All right, everybody come up and walk by the beam. Yep, really. Come up, walk by the beam, put a little load in the middle, and then move on. Just push down on the beam, move on. So someone else, come on, keep moving, keep moving. Move, take that off of there. I didn't say put a load on it. Or maybe I did. Yeah, just press down on it. How resistant is it? Keep going, walk through. Yep. How's that resistance? Is that how you're gonna build your floor in your house?
Yeah.
Yeah. All right, you're gonna come back. Come on back here. Keep going. Now we're in the strong position.
Yeah, unless you do that.
Don't push. Just give it a pull. Any difference? In the strong position. Yeah, about 4 times difference, if not more. Yep, I'm trying to hold it. You notice I'm holding it from rotating, because anytime we get a tall member, it wants to rotate. That's a different problem, rotation. All right. That's inertia. If you build a really cool shape like this, right? Maybe a T shape, or maybe this. What's this called? An I shape. It's actually not. That's what the general public call it. It's a W shape for us. A W shape, yeah. W stands, I know, I'm sorry, but welcome to engineering. It stands for wide flange. So this is a wide flange. We do have I-beams, but I-beams look like this. They're super tall and they have a tiny little shape. And we started with I-beams in this country. That's what we thought was like the cat's meow, man. It was the best. Well, the problem with I shapes is they want to rotate. When you load the heck out of them, they just want to go and rotate. So we fought that with developing wide shapes, and now we predominantly use wide shapes.
Like a ratio rule that separates.
Not really, but it's so obvious. Like when you see the two side by side, it's like, oh, the I-beams, their flanges are so tiny. Like we get so much load out of this web. This is called a web. We get a ton of load carrying capability. That's why we did eyes, right? We can just carry so much load. The further you get away, what are we cubing? The height. So the bigger the height, the more resistant to bending. Like it was simple. We just make these things super tall and we can resist a whole crap load of bending. And then they were like rolling over and failing. It's like, how do we resist that? Oh, that's rotation. We make this wider, right? It was trial and error, believe it or not. Some of that in the beginning. All right, so let me do C. C is super simple. C is the distance from the geometric center to the outermost fiber. Yep, that's it. So you have to know your cross section. And you have to know where the geometric center is. That's not always easy. If it was a T shape, where's the geometric center of a T shape? I don't need somewhere. I need to know exactly where it is, right? Yeah, no, there's equations for it. Centroidal equations for all kinds of shapes, right? But it's right in here. And this is actually an asymmetrical shape, not symmetrical. Symmetrical, right? Top and bottom the same. Symmetrical, top and bottom the same. Oops, not symmetrical. So what we're looking for is the largest C value, right? Because if we're going to bend something, I don't really want to break it. I'm not going to break it. But if we're going to bend something, what's happening to these fibers down at the bottom? Careful, what's happening? Just think for a second. Down here at the bottom, they're compressing, and the top ones are stretching. So we want to know the largest distance because that's the one being impacted the most. That's where the cracking and failure will begin. And those are the little fibers we care the most about. So that's why we want the largest C distance. Okay. If we're doing straight bending stress, then we might, or if we're doing, straight tensile stress. So tensile stress is taking fibers and like pulling them apart, right? Compressive stress is pressing them in, and fibers will react differently to both of those. So those top fibers, even though it's called bending and we're gonna do a bending stress failure, they don't fail in bending. The little fibers don't bend. They literally just tear apart due to bending, right? So these little fibers at the bottom are gonna just like shred apart, and then the whole thing's gonna break and everyone's gonna say it failed in bending. Where it didn't. The little particles literally just tore apart. That's tensile, right? Anyway, all right. So that's C. It's in inches. So this is in inches. This is in inches to the fourth. C is in inches. This is in inches to the fourth. We just need this crazy torque. Okay. Torque is the moment. Moment is inch pounds. That's how we collect a moment. So we just have to be able to figure out, like, how do we calculate a moment? Like, we need these inch pounds. How much is this trying to rotate, right? So it's not, it's static, but it wants to rotate. It wants to do this, right? It's going to bend. That is a rotation. The ends rotate. Okay. The way we calculate it is M equals force times distance. Hang in there. This is nothing. You're going to have 2 hours of this kind of crap, and it's brutal. You're going to like focus that whole 2 hours. You'll be exhausted and you'll be confused. Yeah. Yeah, maybe, unless I just keep going. I got to get moment in and then I can let you go, man. And you want this. This is important stuff. Exactly. Welcome to engineering. This is the beginning. This is the simple stuff. Wait till you get enthalpy and entropy. What? What do you mean? You'll take like 3 thermodynamics classes. It's crazy. All right. Force times distance. That's how you get torque. So force could be 2.25 pounds. That's our load. And then it's acting at these supports. It's trying to rotate around that, and it's trying to rotate around that. It wants to go, correct? And these are allowing it to rotate. It's not fixed. When you push down, those ends curled up, didn't they? Yeah. So we didn't fix these ends. So this force is multiplied by that distance, 4 feet. So it's 2.25 times 4 feet. And this is pounds. And that gives you foot pounds. And then that can go into there. No negatives. Not doing negatives. Okay. Basic calculation. Now, we do have a problem with units, don't we? Because we're what? Inches to the fourth, and feet. Yeah, foot pounds. That's not going to work. So the foot pounds has to be converted into inches to inch pounds. Then you're going to have inch pound, inch, right? Inches squared pounds on top. Stay with these units. Agreed? Inch squared pounds on top. Inches to the fourth on the bottom. What happens to the inch squared and inch fourth? Cancel. We end up with what down below? Inches squared. We calculate this and we compare it to this. And we have just done a structural analysis. Holy smokes. Statics class in 1 hour or less. You should be confused. I get that, but hopefully this is kind of enough to get you like, oh, we can kind of limp along into a structural analysis document. You got a week and a half to find me and say, okay, I got part of that, but we're confused on this area, and then I can clear it up for you, hopefully. Cool? All right, nice job. That I'm serious. That is a small snapshot of what your engineering education is going to be like for 4 years. You're going to come to statics class and you're going to get massively confused. Then you go away, you try to clear that up, and you come back and you get massively confused again. Welcome to the wonderful world of engineering. No one else can do it. That's why you're here. The rest of them can't do it. They're in archaeology class. I don't know what else they're doing out there, but they're not doing this stuff.
Maybe they're the standard setting.
Maybe they're the smart ones, Ruben's like, let the engineers figure that out. Good job, everyone.